This is lecture 13, example 1. What we've been looking at is how to really implement these instructions on the underlying hardware in preparation for experiment 5. So experiment 5, we're going to assemble a working computer, which means have it execute some instructions, a limited instruction set, which means we need to know how to implement these instructions. So the control unit are given to you. This is essentially the information we're going to go over in this example. It's stuff you need to put in the control unit, or we'll say stuff that the control unit provides. Okay, so these are four instructions here. We want to see how to implement these, give a feel for how they're implemented in actual hardware. And let's do this. So what we're interested in is the control signals on these. Okay, so this is our first instruction. I got it down here. And what we know about this is that these instructions require, most of them anyway, require two clock cycles to execute. So this is not a load type instruction, so this instruction 2 requires 2 clock cycles. That's going to be a fetch and an execute cycle. Fetch cycle is nice because it's exactly the same for every single instruction, so we're not really that interested in it. Essentially, the fetch cycle is a matter of doing one thing, and that's asserting this signal right here. So when we assert that signal, essentially it's a read enable for the program memory. Okay, got this right. It's this one. It's read enable for the program memory, and that allows the data at address provided by the program counter to appear on this D1 output here, which is the instruction bits. So what we're more interested in is execute cycle and what we have to turn on in the execute cycle. So this instruction general, you can see it's an add instruction. It's a 3-register add instruction, and it's adding the value in this register plus the value in that register, and it's storing it in this register. And it's doing it with this hardware here. So check it out. We know we're getting these values out of the register file, and so the very first thing we have to do here is get this data into the ALU, which means we got to turn this mux on. So we'll say this mux is equal to 0, because that allows that path of data into the top part of the ALU. Now this is the notion here is that it could be 0 or 1. If I choose 1, it chooses this input there, and that's not what we want. We want to add the contents of 2 registers. One of them's RS1, the other one's RS2. So this source B here is going to equal 0, 0. And so that gets us the data into the ALU. ALU is a combinatorial circuit. Data feeds around here, and you need to get that data back to the register file. And so here comes the result. It's coming around here, and it's going into this mux right here. So RF, this value right here needs to be 3 to get that data in here, and then inside the reg file I need to turn this red right on, so this needs to equal 1. And keep in mind that this source A and source B, here they are, they're coming out of the and also the RF signal, these are all coming out of the control unit decoder, whereas these other signals like this right enable up here is coming out of the reg right here is coming out of the control unit state machine. So if you look at these things, this is also part of the fetch cycle. It's coming out of the state machine also, and we'll say some other controls on this. As you'll see, it's a little bit confusing now, so we're not going to really go over it. When I turn the PC write on, PC write is turned on such that the new value here is loaded after the fetch cycle. So we'll see that more clear in another full timing diagram. And essentially that's about it for this instruction. And you'll see the next instruction is very much the same. And here's the next instruction. It's also an add instruction, but it's adding an immediate value to a register. So this is RS1. So source A is still equal to 0, but this immediate value for the other register, which is it's not coming out of a register, I need that immediate value into this thing. And so what we're going to do is we're going to look at the instruction. We're going to see it's an I-type instruction, and that's the I-type value I want to put in there. So source B is, of course, 0, 1. Yeah, and guess what? For the last problem, I forgot to fill in the ALU operation. They're both adds. I know it's a 0, 0, 0, 0 because I look at this table up here and I can put in the select bits. So other than that, other than this change right here, this is the same as the 3-register add instruction. So very much same. Once you implement one, it's very easy to implement the next one. And so what you'll see here is the results still going into here, which is 1, 1. And I need to write it, which is a 1. And so that's the add immediate instruction. Once again, the only difference being is with the second operand. In the add instruction, it was a register. In the add immediate instruction, it's going to be an immediate value. I know that add I is an immediate type instruction. It's an I type, and that's what I'm going to use as the operand there. Okay, so this is the load word instruction, one of the more complicated instructions, essentially because it's a 3-cycle instruction, but it's not complicated, it just has some extra simple stuff to it. And so what this is a load word. It's a classic memory to register transfer. So it's taking something from the memory, putting it into a register. And so anytime you do a memory access, you need an address. So this uses these two values here, which is this is the offset and this is the base register. It uses those to create an effective address by adding those together. So it adds the value in x20 to this offset here to perform an effective address. So this addition is actually done in hardware. It's done with the ALU. So for right away, we know that during the execute cycle, we are going to do an addition. So we're going to, once again, we're going to do that add from for the ALU function. Okay, so this offset value here is actually the immediate type, and this is actually RS1. I know that from looking at the spec, and so essentially RS1 goes into this register, which is going to be a 0, and then let's see, this is L, the load type instructions, which I looked up, and sure enough, it's an I-type instruction. I had to look it up. I didn't really know what it was, so I need to select a 0 and 1 to get the that immediate value to add with the base register. And what's going to happen is it's going to come over here and be used as an address into memory. So this result is going to be the address into memory. So another part of this execute cycle of instruction is to turn this read enable on. And so that's essentially right there is the execute cycle. Now it has a write back cycle. So what's going to happen with the next clock cycle is it enters write back cycle. The data is going to be available on this DOut2 here, and I need to write that data to the register. So two things have to happen during that write back cycle. Is I have to turn this read write on, which you've seen before. There's my 1, and I have to get this data transferred over, which is from memory into the reg file. So I need to turn this on. So this equals 1, 0. So it's 1, 0 to get that. Let's see if that's right. To get that data through the 2 input on the mux. And so that is our load word instruction. All the 5 of the load word instructions are very, very similar. In fact, you'll see that they essentially are exactly the same if you think about it, and then a lot of the details are handled by the memory unit, but that's a story for another lecture. Last instruction here is a jump and link. Jump and link instruction kind of highlights one of the things we haven't really been looking at. Essentially, a jump is an unconditional branch, however you want to put it. And so essentially what it's going to do is jump to a location associated with that label. So the label itself is just an address, and that's the address I need essentially of where I'm jumping to. So I need to load that into the program counter over here, which I'll do. And so it looks good. It looks like a very simple instruction, but then you suddenly look at the manual here, and what you see here is in the spec, you see PC gets PC. Nope, that's not right. XRD gets PC plus 4. Okay, so essentially that's part of the spec also. So essentially that's taking the current PC value, adding 4 to it, and loading it into a register. So it's very important. That's how we handle subroutine calls. But it's not really apparent from this instruction. I got to look at the manual and get this thing. So for this instruction, the execute cycle, I am going to do a couple things. So we kind of skipped over PC source and all the other instructions. It was 0, but in this instruction, this is the JAL instruction. PC source has to be 1, 1. Additionally, just like all the other instructions, every single instruction as part of that execute cycle, I'm going to a 1. So essentially, every single cycle, every single instruction, I'm always loading the PC write. Okay, essentially, I'm asserting the PC write. I'm loading a new value into the program counter, whether it be the next instruction, which is PC plus 4, or one of these other 3 values. These other 3 values handle the branches, particularly unconditional branches with the jumps, and just the branch is a generic branch. This instruction uses JAL, essentially means I just need to select the right PC source for this. Okay, all the other instructions, like I said, I didn't go over them. They all assert the PC write in the execute cycle, and they are choosing the next instruction because it's not a program flow control instruction. So the other part of this instruction is I need to take that PC value here. PC value, you can see PC plus 4. I need to get that into a register, which means RF select here has to be 0, 0. And I need to turn this, the reg write on, which needs to be 1. Okay, so that, once again, this is the other part of the instruction that it's not overly apparent for this jump instruction, but it needs to be in there. Don't forget about it. So in summary, every single instruction is loading a new value into the program counter. If it's not a program flow control, it essentially is going to choose the PC source as 0 to choose the PC plus 4 to go into the program counter. And we'll call that done.